Thank you everyone for joining us today and welcome to GOWIN'S webinar series conducted in hybrid format. Today's presentation is USB 2.0 Soft IP, an introduction to GOWIN Semiconductor's USB solution for FPGAs. My name is Scott Casper with GOWIN and I'll be your moderator. Our presenter today is Grant Jennings with GOWIN Semiconductor. Please feel free to send us questions via the question or chat button throughout the presentation. We will answer them at the end. Our agenda for today will be as follows: speaker biography, introduction to GOWIN Semiconductor, USB 2.0, GOWIN Soft IP USB interface solution, followed by a live question and answer session. A bit about our speaker. Grant Jennings is Senior Director of International Marketing at GOWIN Semiconductor, focused on strategic solutions for programmable technologies. He has over 12 years of FPGA system architecture experience in areas including ASIC prototyping, interfacing, bridging, and hardware acceleration. Grant received his electrical engineering degree from Iowa State University and his MBA from Texas A&M University. Now a brief overview of GOWIN Semiconductor. GOWIN was founded in 2014. Our executive headquarters is located in San Jose, California, and our operational headquarters is located in Guangzhou, China. We have over 160 people employed in R&D, engineering, and administration. We serve the low to mid-range density markets for FPGA needs from 1,000 LETs to 100,000 LETs. For more information about GOWIN Semiconductor and our latest innovative products, please visit us at gowinsemi.com. At this time, I'd like to start our main presentation.
Hey everyone, welcome to the USB 2.0 Soft IP webinar, an introduction to USB 2.0 solutions for GOWIN FPGAs. My name is Grant Jennings. I'm the Senior Director of International Marketing for GOWIN, and I am extremely excited to do this webinar because this is a long overdue IP for the FPGA community, and GOWIN is the first to bring it to market. GOWIN's the innovative FPGA company, and we are extremely excited to offer this to our customers and product developers. So let's go into the agenda. First, I'm just going to give a high-level GOWIN product summary, and that will include some new items coming to market. Then we'll go into just a high-level USB Universal Serial Bus overview. Then I'll talk about USB interfacing specifically with GOWIN FPGAs, as well as why USB integration is so important for FPGAs. Then we'll go into GOWIN's USB solution portfolio, and that will include information on the USB 2.0 PHY and device controller IP, as well as some block diagrams and some resource utilization numbers. I should note that we also support USB 1.1. That includes the USB 1.1 PHY and USB 1.1 device controller. And there's certain benefits that I'll discuss on why you may want to use one or the other. I think it will be clearer later in the webinar. Then we'll go into some use case examples that we're seeing in the market, as well as some future examples of things that you may be able to do that may be interesting. We'll go into the development boards that are available and upcoming from GOWIN that offer the USB 1.1 or 2.0 interface. And then I'll just briefly discuss our design services program that's ongoing and ongrowing, and I'll offer some resources that are available generically for USB, but then also for GOWIN's USB solutions. First, let's talk about GOWIN's product portfolio of semiconductor devices. GOWIN primarily sells traditional low-density FPGAs, and these come in two forms. Our N series is our non-volatile FPGAs. These range from 1 to 20K lookup tables and include embedded flash. These are very small form factor, low power, and low cost FPGAs for end products from consumer, industrial, medical, automotive markets. Then we have our traditional volatile FPGAs, which is our A series. These include FPGAs from 20K lookup tables to 55K lookup tables, and they offer a best-in-class performance over cost ratio. Then we have what really differentiates GOWIN from other FPGA manufacturers, which is our hybrid FPGAs. We offer an S-series FPGA product line, which includes FPGA fabric along with a hardened Cortex M3 microprocessor. We also have an R series, which is an FPGA with extended user memory. And these come in various forms. And I should mention that all of these series are typically combined. So in the R series, we have various devices ranging from 4 megabytes to 16 megabytes of extended memory within the same device package. And then in our S series, we also have a NSR series or an SR series, which not only includes the hardened Cortex M processor, but includes the extended memory as well. So just note that these series that I'm referring to can be mixed and matched. Then we have our E series. This is our security-based FPGA product lines, and this allows for asynchronous key pair generation based on PUF technology. And if you don't know what PUF technology is, it basically uses intrinsic properties of the device's, the semiconductor device, in our case SRAM, to generate a unique key pair for that device that cannot be recreated. Then we have our RF series, which is an FPGA, MCU, as well as a Bluetooth low energy transceiver, all in the same device. So you maximize the types of programmability that you can do, and then you also add wireless within the same chip. I should mention on the RF series, we also have certified Bluetooth transceiver modules. So one obstacle with Bluetooth and Bluetooth low energy is that you have to certify whatever circuit board the device sits on. And so modules are often common that are already pre-certified, and we of course have those for you. The next series, this is a new series, but it's a FPGA series with 2.5 gigabit per second per lane MIPI D-PHY hardcores. So if you're not familiar with MIPI D-PHY, it's a video interface, typically for mobile image sensors or mobile influenced image sensors, as well as mobile displays and mobile influence displays. So this is very popular in the consumer mobile space, but also very popular in the automotive space as well as industrial. Anything that uses a camera or a display, MIPI is a very important interface, and we support 2.5 gigabits per second per lane. That means 10 gigabits per second per PHY, and you can do multiple PHYs as well. So then we have our automotive series devices, and these are labeled as an A speed grade. So there's multiple devices that are automotive qualified with AEC Q100, and you'll just see on the speed grade, you'll see an A in the speed grade. So that's new also. And then something very new that was just released is we have the start of our ASSP product line. So these are application-specific products, application-specific semiconductor chips. And the first product line within our ASSPs is our GoBridge ASSP product line. So these are ASSPs that perform a bridge interface from one interface to another. And within the GoBridge ASSP product line, the first two devices to come out is our GWU2U, which is a USB interface to UART interface. So you can convert USB to UART. And then the second device is our GWU2X, which converts USB to many different protocols, including JTAG, SPI, I2C, and GPIOs. Now let's talk about Universal Serial Bus and discuss an overview of each specification, the encoded line rate, and the application purpose. USB 1.0 was the first specification offering low-speed USB at 1.5 megabits per second line rate. This was mainly used for control and configuration of peripherals. It was quickly superseded by USB 1.1, which offered full-speed USB interfacing at 12 megabits per second. This not only could be used for control and configuration, but was high speed enough to offer communication paths between devices and the PC over cable. Shortly after, USB 2.0 specification offered high-speed USB at 480 megabits per second line rate, which allowed for data acquisition and data streaming. Following that, USB 3.0 and 3.1 offered encoded line rates of 5 to 10 gigabits per second. This offered raw data pipelining for primarily hard drives, external hard drives. So as you can see, the speeds increase as the specification numbers increase. One thing to note between USB 1.1 and 2.0 is that the speeds of USB 2.0 basically required a CDR, a strong CDR, and hardened PHY to be added to a lot of these devices supporting USB 2.0. So there was a cost associated with including the USB 2.0 interface on a semiconductor device. And same with USB 3.0 and 3.1. The difference between 3.0 and 2.0 is USB 3.0 and 3.1 is actually just USB 2.0 with a separate sideband channel, meaning there's separate wires in the cable that supports a raw data pipeline of 5 to 10 gigabits per second. So USB 3.0 actually has a USB 2.0 interface and then another interface that's really similar to a single channel PCIe port. So that adds, the reason why I bring this up is that each of these specifications, although the data rate increases, the cost also increases. And so particularly everyone's kind of aligned to USB 2.0 and 3.0 or 3.1. However, particularly on the device side, USB 2.0 still has a lot of room to grow and to be used, because on the device side, you're only going to use 3.0 or 3.1 if you really need high bandwidth data pipelining and raw data, not encrypted or encoded or compressed data. And so the applications there's still value in 2.0 because the cost of that interface from a semiconductor perspective is dramatically lower. Now we'll go into USB interfacing on GOWIN FPGAs. So here's a block diagram, high-level block diagram of the IPs that we're offering for USB 2.0. And so we offer a USB 2.0 PHY that is inside the device. This is very different from, at this time, any USB FPGA solution that you're going to see on the market, because all of them, if they offer USB 2.0, they're all handling USB 2.0 with an external USB 2.0 PHY. And there's a fairly high cost and power profile associated with that solution. So what GOWIN has done and what this introduction is all about is our USB 2.0 IP that is integrated within GOWIN's GW1N non-volatile product line, as well as the GW2A series FPGA product line. So this is a super important integration IP for the FPGA world. We also have the USB 2.0 device controller, and this device controller has a UTMI interface, so it can be used with an external USB 2.0 PHY or an internal USB 2.0 PHY, which only GOWIN offers. So this handles the packet handling, removing the packets, from the payload, or adding the packet headers and checksums to the headers or to the footer, and also initializes the USB 2.0 line interface, and then also handles the basic transaction handling. And basically on the other side of this IP, you can just feed the USB 2.0 device controller raw data from your own design. And so you can make a completely unique USB 2.0 chip in real time with GOWIN FPGAs. So why is USB integration on FPGAs so important? Well, it really falls into three categories. The first one is BOM cost and BOM footprint size reduction. We see a lot of USB solutions that we look at a PCB design and we see multiple chips that an FPGA could handle each function separately. And so then if an FPGA can handle the functionality of each of these chips, why not combine them? That makes your board more reliable, it lowers the cost, and it provides a much higher quality solution. It also lowers the power of the entire PCB and the total solution. So just in the diagram, just going to the diagram, you can look at kind of a generic example that we see a lot of time. You have some sensor or some controller. This could be an image sensor, it could be an ADC, it could be a microphone array, it could also be a display, it could be memory, it could be a lot of things, but you have some either sensor or thing that you want to control. And then you have a series of chips that all do different things. So it's very common to have an interface bridge. Maybe that sensor or that controller doesn't have the same interface as your processor, and so you need to convert one interface to another. And so you'll have a bridge chip just specifically for that. Then you'll have a processor that does some processing on the data, as well as potentially an encoder or a decoder. This is to reduce bandwidth and storage size. And then lastly, you'll have this USB 2.0 discrete bridging device that is taking that processed and encoded or decoded data and transferring it to a host device over USB 2.0. And so if an FPGA can do all of these things, we talked a little bit about USB bridging, interface bridging, but FPGAs are really good at reasonably high-speed data pipelining, which means that they're excellent for things like video streaming or high-speed data acquisition. So converting from something like MIPI D-PHY, MIPI CSI2 or MIPI DSI to a parallel interface or parallel to CSI2. These are very common things that FPGA has a very strong niche market for, because the data rates are often higher speed than what a microprocessor can do and are too expensive to do with an SoC, as well as the latency is too high to do with an SoC. With a gate array, you can provide a low latency, high speed, interface conversion. Next, you have the processor and encoder, which, as I mentioned, we have a hardened Cortex-M series device, and we also have many soft cores, both RISC-V and Cortex-M soft cores that are available free to use within our IP portfolio. So that part is often covered in FPGA designing, and we offer that in our IP portfolio. Then the encoder is typically something that needs to be a hardened block within your processor. So you have to find a processor that has the encoder or decoder that you need. So for example, an MJPEG encoder or decoder for video is often very important for doing USB interfacing with video. So that's something that an FPGA can do, and you don't need a specialty portion of an ASIC to do it. It can do it with its gate array, and it can do it in real time. Lastly, you have the USB 2.0 interface bridge, and this is where the roadblock for a long time was. But now, with GOWIN's USB 2.0 PHY and device controller IPs, this is no longer a challenge. And so all of these three components can be combined into one single low-cost, low-density, low-power chip and provide a BOM cost and footprint reduction into a single device. The second point as to why USB integration on FPGAs is important is that USB 2.0 has been around for a while, right? So a lot of these device bridges for USB 2.0 are actually going end of life, and it's making second sourcing very difficult because there's still many devices that need to be very low cost. 3.0 is too expensive, and their bridging device that they used to use is very soon not going to be available. And so not only does GOWIN's FPGA solution provide a more advanced process node than what is typical on some of these USB 2.0 device bridges, but it's going to be around for a long time. And the great thing about an FPGA solution as an IP is that as GOWIN releases their next generation FPGAs, this IP is transferable and can be used with them as well. So your second sourcing support, if you go to a GOWIN FPGA solution, is forever. The third point is product enhancement and flexibility. So just in the solution where we took three components and reduced it to one FPGA, you can also use this as a flexibility point to enhance your solution over time. So first, you can just do this BOM cost reduction and get a great benefit from that. But if you have some resources left over, or you decide that you choose a FPGA footprint that is compatible with our larger density devices, which is common if you plan ahead, that you can choose a package that maybe you have a lower density device, FPGA device for now, to just do, let's say, the bridging, the processor, and the USB 2.0 interfacing. But then later you can advance to maybe a larger FPGA and include the MJPEG encoder or an encoder to do compression, to do higher video streaming rates. Is a great example. So FPGAs allow you to kind of future-proof your solution and allow you to enhance the solution over time just with software, just with firmware and bitstream updates. GOWIN's USB solution portfolio is growing and will continue to grow. We're a member of the USB Implementers Forum, and we have active solutions, as I mentioned, for USB 1.1 and 2.0, and those are included in our IP core generator within GOWIN EDA. So if you download GOWIN EDA, it includes an IP core generator which allows you to generate the USB IPs. These IPs include USB 1.1 soft PHY, USB 2.0 soft PHY, and then a USB 1.1 or USB 2.0 soft device controller. And all these IPs are free of charge. So if you're using GOWIN FPGAs, you're using GOWIN EDA, you can generate these IPs. We don't charge for any of the IPs that are in our IP core generator. This is very different than a lot of other FPGA manufacturers. We also offer a USB Type-C power delivery solution, so you can combine your USB 1.1 or 2.0 solution along with Type-C features with that reference design and IP. We also offer, we're working on offering higher level USB class support. So things like USB video class, USB audio class, these kind of common features at a higher level that are needed and required and not so trivial. We're working on those, supporting these classes with USB 2.0 mainly, and also the driver support that needs to be there to do these type of applications. Also, we have the GoBridge USB to peripheral ASSP product line that I believe has just been announced, and that includes bridging USBs from USB to UART, JTAG, SPI, I2C, or GPIO, and there's no FPGA programming required. These are ASSPs, so they're pre-configured with all the firmware that needs to be there. You just put it on your board. We provide a C++ API to develop your own solution, but also within GOWIN Programmer for, let's say you're doing USB to JTAG, we're actually using this chip for our next generation development boards. So we're using it to program our own FPGAs, but you can use it to program other manufacturers' FPGAs. You can use it to program microcontrollers. You can use it to program flash components with SPI. You can use it to interface directly with sensors like accelerometers or anything with an I2C interface. So it's a great ASSP to have in the portfolio, and not only do we offer it to GOWIN customers as a semiconductor product, we actually use it ourselves for our development boards. Just a little bit more on the USB 2.0 PHY and device controller IP solution. So again, this is a brand new interface solution to the FPGA market. It's, as far as we know, never been done before. As far as I know, I've never seen it before, but I've seen the demand, I've seen the need over the years. So this offers an alternative solution. Instead of using external USB PHYs, you can just integrate the PHY in the FPGA. GOWIN offers the USB 2.0 soft PHY, which provides integration of the PHY itself in the FPGA. This is a patent pending implementation, and the way it works is it uses GOWIN's flexible high-speed FPGA I/O to deserialize and to perform clock data recovery on the encoded data. No external PHY is required to perform USB 1.1 or USB 2.0 connectivity with GOWIN FPGAs anymore. You can do it if you want, but you can also integrate it, and I'll show the resource utilization on the next slide. Support for all GOWIN FPGAs, so this includes the 1N series as well as the 2A series. And what we've seen is there's, solution demand is all over the spectrum of our product lines. So, there's some solutions that just need a very low density FPGA to implement these solutions because it doesn't take that many resources. It's mainly a solution that requires the right I/O in the FPGA. But then we've seen a lot of customers graduate up into, the 18K or 55K solution area because they want to start integrating some additional features. And one unique thing that I haven't covered yet is that with this solution, you can not only have one USB 2.0 interface, but you can have many USB 2.0 interfaces, as many as I/O permits on the package you choose. So now we move on to the USB PHY and device controller IPs, a little diagram with some more detailed lower level blocks. And then I think the important thing on this slide is the upper right-hand table. So this is a table of the resource utilization for the USB PHY plus the device controller in either 1.1 or 2.0 mode. So the device controller itself can do 1.1 mode or 2.0 mode with the same device controller IP. So it supports both. The PHY is separate. So the 1.1 PHY is separate from the USB 2.0 PHY IP. And there's a reasonable difference in the resource utilization. So this is an important piece of information that there's value if you're not doing high bandwidth transfers of, say, video data or streaming data, maybe high-end audio data. If you can live with the 12 megabits per second line rate minus the encoding, I would stick to USB 1.1. It's a little bit simpler. It uses less resources, both in terms of lookup tables as block RAM, and it's just an overall more simplistic solution. But if you do need the throughput, then the additional 700K lookup tables and a couple more block RAMs isn't too bad. So these are kind of the two options, and we see needs for both of them, and so we definitely continue to support both. So now I'm going to go into some high-level use case examples. The first set is just examples of simple peripheral bridging, and these peripheral bridges are actually covered in the ones listed here are covered in our ASSP product line, the GW U2X and the U2U. But if you want to do something beyond what the U2X and the U2U do, just going from one USB interface to one SPI interface, then we have all the IPs available to do that in our FPGAs. So for example, if you wanted to do USB to multiple SPI ports, or more than 16 GPIOs, or more than just one I2C port, you can do that with our FPGA designs and our FPGA IPs. But if you just need a simple USB to SPI or GPIO or JTAG interface, probably the ASSPs are the better place to start. So now another use case. This use case is super popular and has very high demand. This is a MIPI CSI2 to USB 2.0 solution. So this is an example of something that you can do in the FPGA, and we're actively working to design the solution in a broader solution context. So I would envision at some point we have a IP portfolio or a reference design with exactly this solution. As of right now, we have several customers that are implementing exactly this with the USB 2.0 IP solution. So we have CSI2 reference designs and IPs. We have USB 2 now, and this provides a great way to bring in image sensor or camera data into your PC or smartphone, whatever your USB host is, over USB 2.0. And then we even are going a step further internally in exploring the use of an MJPEG encoder to go beyond the resolutions that are possible with just raw data streaming. So we've seen, capabilities into the 4K region with some heavy MPEG compression, and FPGA is great for those type of solutions because the MJPEG encoder needs some real-time processing, real-time pipelining of the data. You can't do it with an MCU. You can't do these interfaces with an MCU, and so this is a differentiator for FPGA solutions. So on the other side, USB can go ahead and target a display, and I've got two examples of where this might be something very interesting. So again, these are just examples. These aren't reference designs that we have yet, but I expect that these will grow over the time that we have the USB 2.0 PHY and device controller solution available. So these are kind of predictions, but it would be very probable that these examples turn into reference designs. So in this case, we're going the other way. We're going from USB 2.0, we're streaming data in, we're potentially decoding it if it was compressed, and then we're just sending it right to the display. And that's the upper left-hand block diagram. In the lower right-hand block diagram, we're actually developing kind of a graphics processor or a display controller where you have maybe sprites or maybe some graphics processing capabilities like draw line, draw square, draw circle, these kind of basic capabilities, overlay capabilities, things like that. And you just basically send the commands at fairly high speed to drive this graphics processing design that you have in the FPGA, which will eventually drive the display. Another broad term example is utilizing our GW1NRF FPGA, which has a embedded microprocessor hardened as well as a Bluetooth low energy transceiver. So in this case, you can actually convert USB 2.0 to and from BLE, which is great for dongles, but not only dongles or something simple, you can add some additional processing capabilities either in the MCU or the FPGA to do things beyond just the simple BLE to USB dongle. Another area that I find really interesting with use case examples is security and USB 2.0. So here's just an example of something that maybe somebody would want to do where they've got a USB 2.0 interface and maybe they're storing some data either in flash or RAM, and they want to do authentication to make sure that they're talking and communicating with the correct PC or authorized machine on the host end, and they may want to do some sort of boot security of some data in the flash. Maybe they do some check that the flash hasn't been tampered with before they send the data over the USB pipeline, or vice versa. Maybe they check the data after they load it to the flash so they make sure that it hadn't been tampered with or there wasn't a man-in-the-middle attack on that flash part. So you can utilize our puff-based security library to do these functions, and you can do that you can utilize internal flash or internal SRAM, or you can even go to external flash, and with the asynchronous key pair generation, you can actually secure that external flash as well. So no issue necessarily with having it external. Okay. Now, let's do another use case example, just kind of a generic example for high-speed data acquisition. So, there's several high-speed data acquisition cards. Some of them use multiple chips for USB and for their data handling. So, in this example, we have a high-speed ADC that's going to some sort of memory controller, and then that's throwing some data to one of our devices that has the embedded PS RAM. So, we have up to 16 megabytes of embedded memory depending on the device you choose. And so you can take some high-speed data, bring it into the FPGA, store it, and then run it to the other side on USB 2.0 after some, if you want to do some pre-processing in it or you want to pick and choose certain data. These are definitely things you can do, and so this is just a great example of utilizing the extended memory for a data acquisition example. Lastly is a USB use case example of a multi-port USB hub. So we have the USB 2.0 PHY, we have a USB 2.0 device controller. What about the host controller? If we had that, then we could do multi-port hubs with a single chip. Well, actually, we do have a starting point for that, and we're just kind of feeling out the interest if that's a direction that would be interesting to go. We think that the device controller is probably the more popular choice for our USB solutions, but we do have a clear path. In fact, we basically develop a host controller in a lot of our simulations for the device side. So we have a host controller, and we'd be very interested if these solutions develop and provide a path to offer that as an IP as well. So please, these are examples of some of the things that we're seeing, some of the predictors of examples showing what you can do with this new capability on GOWIN FPGAs. Please feel free to drop us a line of any use case that you would like to do or you think might be possible based on this information, and we will try to help you as best as we can. This is a pretty broad solution and it can be used for a lot of things, so there's no such thing as a silly solution here, because that's the purpose of FPGA Fabric, is that it allows you to be creative and be able to utilize silicon in real time to do some amazing, new, unique capabilities and applications. So we absolutely encourage your input and your questions on what is possible. So now let's go into development boards. We have a few different options for you, and the first one starts with a modification to the original GW2AR18 DK start board. We basically call this the DK USB GW2AR18 development board, and it's just basically updated. It's the same board but adds the USB 2.0 port. And for this board, we've been using it internally. We have some customers using it, and there's limited supplies available of this board. But if you've got something ready to go, you're really interested in developing a solution with our devices, let me know, and we'll see what we can do to get you one of those boards. Additionally, we have another development board, which is our DK USB multi-device board. This includes a 4K, I think our GW1 and 4 device, as well as a GW2AR18 device, and it has a variety of different things that you can do with it. So it has an external PHY that can be utilized with the 4K or the 18K device, and it has the internal PHY interfacing to do the internal PHY as well. It provides options for USB 2.0 and 1.1, so you can test out both. And we have some limited supply available now. We're doing a lot of testing, a lot of new developments with this board. It's a pretty nice board, and production of this board is kind of anticipated for Q3 year 2021 for the broad release. Additionally, on the GoBridge ASSP product line, we have some USB dongles, USB programming dongles, which allow you to basically take the USB interface, and then it provides a 0.1 inch header to do fly wires for programming whatever you wish to program via JTAG, UART, I2C, SPI, or GPIO. So, for example, you can use this as basically a programming cable for GOWIN FPGAs using GOWIN Programmer. That's a really great use for it. You can also use the USB to UART in the GW-U2U to program microcontrollers or provide a communication path for, say, an Arduino board or something like that. Anything that uses UART, you can use this, and you can actually use it over virtual COM port, so you don't even have to develop any C code, no code, you can just use it. Then lastly, moving on to an upcoming solution. So we see high demand for USB 2.0 with USB video class. So we see the need for a USB camera module reference design, and we're working on that right now. Finally, other resources. So if you're interested in the GOWIN USB 2.0 PHY or device controller IPs, there is a database on GOWINSemi.com, and the hyperlink is provided. That basically provides a link to all of these lower level documents that I also added a hyperlink for. So a quick start guide for that first board, the AR18, the soft IP user guide, the device controller IP user guide, and the device controller reference design. These are all available on GOWINSemi.com, and I encourage you to read through and take a look at that documentation. Also, some outside resources on USB 2.0. So the first one, man, I highly recommend this site. I've been using it for years, is USB Made Simple. It's a great website that goes through in very simple terms all that you need to know about USB, from the physical interface level to the protocol interface level. It's an amazing site. And then followed by that, we have the USB 2.0 specification, which is also great, just more details. And then the USB UTMI interface specification. And I would recommend looking at both of these if you're interested in some of those lower level details. Some of the details in the UTMI specification aren't in the 2.0 specification, and vice versa. And then I just added our GOWIN social media channels. I encourage you to add us or like us on YouTube, Facebook, Twitter, and LinkedIn. This allows you to see the new solutions that unfold. Basically, at least monthly, there's probably a new solution. So I encourage you to sign up, because you'll just see the activity going on at GOWIN. So this is the end of the webinar, and I really appreciate your attendance. I think that the USB 2.0 PHY and device controller IPs provided by GOWIN Semiconductor are very innovative, long time needed in the FPGA community, and I'm very excited to see what solutions and applications and end products are developed with this new capability. So I look forward to helping you go win by programming for the future, and please contact us if you have any questions or need some help in assisting with your next application. Thank you very much.